How's it going? I'm having some... Oh, no, it's fixed. Thought I was having some video issues there. Hopefully everything's okay. Can you hear me all right? Can you see me? Turn up your me. Turn up your me. Turn up my mic. My mic's turned up, mate. Maybe you need to turn up your volume. Having said that, no, my mic's all the way up. It's not going to go up any higher. So it sounds fine to Kira. So George, it's on your end, I'm afraid. Cool. Okay, so don't know how long we've got. Don't know how long you guys want to spend on this. Obviously, with your mocks tomorrow, this is not the time to sort of be learning new stuff, right? This is the time to be asking questions about specific stuff. Okay, so here's what I have on the. This is the what's it called? Tyler is asking for coding. Kira has some pre-prepared. I don't like the phrase pre-prepared, because if something is prepared, it's already it's pre-paired. If you pre-pair, I mean there is no what's before the before. It's a bit of a tautology. So Farrell wants HTML and JavaScript. Ella wants RISC and CISC. Okay. The plan was to maybe have a look at some of the stuff on here. Structure and function of the processor. That's your fetch, decode, execute cycle, etc., etc. Difference between von Neumann and Harvard. Types of processor. That's your CISC and RISC stuff. So we can have a look at that as well. Multi-core and parallel also falls into that bracket. So at the moment, Ella is wanting this stuff. We can go over that. It's not an awful lot to go over there, but we will nonetheless. Input, output, and storage you haven't properly done yet, so that's not going to be on there. System software we haven't done yet. Application generation we haven't done yet. Software development we haven't done yet, right? Types of programming language. You need to know about procedural programming, object-oriented programming, difference between them, all of that stuff. You also need to know LMC, the little man computer. So if that's an area you want to go over, there's that as well. I'm throwing this out there just in case this adds to your list of collections, by the way. Compression, encryption, and hashing, databases, networks, including network hardware, client-server, peer-to-peer stuff, web technologies is your HTML, your JavaScript, client and server-side processing. Data types is converting binary and stuff like that. I'd like to think that you guys are probably pretty hot on that. We probably don't need to go over that, but feel free to tell me otherwise. Data structures we haven't yet done. Boolean algebra, Karnow maps, all of that lot is there. Legal, moral, cultural, and ethical stuff. So computer legislation, moral and ethical issues. And that's it. And then this stuff here, thinking abstractly, the need for abstraction, etc., etc. Thinking ahead, that is all about identifying inputs and outputs to a what's it called, to a system, and being able to trace the flow of a program. Thinking procedurally. That is your general ability to produce a program that is split into like functions and whatnot. All of this stuff, by the way, is stuff that isn't sort of directly taught. It's a case of, hey, we are now using these skills, or we're developing these skills in the pursuit of this particular problem that we are solving. One thing that I will say to you all, obviously programming techniques, that's one of I think that's the main area that Tyler wants to look at. Sequence, iteration, branching. Knowing the names of these things is probably useful. You might look at this stuff and think, oh, what does that mean? But you actually know what it means. It's just like, associating those names with it. We can have a look at that. And then there's the algorithm stuff. The stuff that we did recently, big O notation, computational complexity, all of the searches, all of the sorts, Dijkstra's A star. I'd like to think that because we have done the ethical stuff, the legal stuff, and the algorithm stuff fairly recently, that's probably not the stuff that you really need to go over. But I don't mind giving it a brief revisit. And then everything else is so that's it. There will be nothing on the test that we haven't already covered. So with that in mind, if I'll just make a note here. Tyler says programming, all of it. I don't have enough time to go over like all of programming, so you might have to choose some specific bits. In spirit of data protection, let's not use full names. F's in chat for Mr. Hawks, who wants to do laws. Ella mentioned risk and CISC. And if I recall correctly, Kira said she had a bunch of questions. George wants to see an example run through of the merge sort and the quicksort. Yeah, we can do that. Okay. The marge sort. Merge quick sort. JS Hutml. Right, so in terms of like I can run through LZW compression, but bear in mind you don't actually need to know the specifics of LZW compression, right? Foreign and composite keys. Okay, I'll put all these down. If I just put dictionary compression, I'll put dictionary compression so we can go over. You don't need to know the specifics of how LZW works. That's like outside the scope of A level. When I taught it, I used it as an example so that you could see how lossless compression reduces file size without causing a loss of data. Dictionary compression. What else have you written down here? Foreign and composite keys. So we'll do some database stuff. Port range. Port range hash collision. Okay, so we'll go over hashing. I'm not sure what you mean by port range here. Port range. Do you mean a port range is merely a number of entrances into the system? So, for example, I assume you know what a port is, right? If I have a range of ports, it means that, for instance, I might have incoming port 21 open. I might have incoming port 22 open and 23 and 24. So I could say I have the range of ports from 21 to 24 open. Do you see what I mean? That's all it is. Risk and CISC, yes, we'll go over that, but bear in mind it is with a C and not with a K. Anything else? So far, the list of things that we've got. Programming, I assume you mean both Python and LMC, right? We've got programming, laws, JavaScript, HTML, risk, CISC, merge and quicksort, dictionary compression, foreign composite keys, hashing, bus width. Again, this is a minor thing. So we can, we quickly go over that. The bus width is basically how many bits of data can be passed down the bus at the same time. That's all it is. If you have a bus width of 8 bits, it means that down your bus 8 bits at a single time can go. Differences between Princeton and Harvard. Yeah, okay, we'll go over that. Let's put BN Harvard. Pipelining. I'm gonna say, right, there is a big list of stuff. You're leaving it quite late if this is all stuff you want to go over. I mean, I was kind of expecting sort of specific questions on these things, rather than, hey, can you go over all of this stuff again? Because we're not going to have time to go over all of this stuff in detail. Okay. I can go over it. I just don't know how much time I'll be able to dedicate to it. So if you've got specific questions on it, that would be very useful indeed. Right. Out of all of that stuff, I'll tell you what. The two of you have mentioned risk and CISC, so we can start there. Just bear with me a moment. How are we looking? Are we still, everything's still rosy? Yeah, cool. Sorry, I had to just switch screens there for a sec. Okay. Oh, okay. That's fine, Kira. That's fine. I'm sure it'll be a case of when I explain it, it will just make sense, and you've probably filed it in your brain under something else. So yeah, that's fine. We can quickly go over that. Nay problem. Right. So risk and CISC. Do you have any specific questions about risk or CISC, or you just want a quick overview of them? First of all, do you know what it stands for? Just type in the chat what RISC, R-I-S-C, stands for, and what CISC, C-I-S-C, stands for. Reduced instruction computer set, that would be RICS. Reduced instruction set computer. Reduced instruction set computer. Now you will, it's unlikely that you'll be asked to specifically say, hey, what does this acronym stand for? It's more likely, I'm unsure on the differences between fixed and floating point binary. Risk and CISC, I wanted to know some real world examples and applications. Okay. Cool. Yeah, so reduced instruction set computer and complex instruction set computer. It's just two different types of architecture. Okay, let's skip over this slot. Remember this? Oh wow, it's been a while since we did this, eh? Right. Okay, so we can have a look at pipelining at the same time. Let's skip over the control bus. Way there he goes. Not going to do that joke. Do you remember that joke? Anyone remember that joke? It was knock knock. Who's there? It doesn't work with one person saying it, because like you say interrupting cow, and then interrupting cow who moo. Because that was a bit where I talked about interrupts, and I'm assuming that's because no one has mentioned interrupts. You know what interrupts are. Right. So let's talk, I tell you what, because it's first in my presentation, let's talk about the difference between von Neumann, or Princeton architecture as it is known, and the Harvard architecture, or the Harvard architecture as they say in Harvard. So just so that we're clear, the architecture that I taught you the fetch, decode, execute cycle on, that is the von Neumann architecture or the Princeton architecture. The exam board will refer to it as the von Neumann architecture. Okay, so anything where you have the memory store and you are fetching instructions from the memory store, and then either fetching data from the memory store and or storing data in the memory store, just like we did when we learned the fetch, decode, execute cycle, that is the von Neumann architecture. Okay, so Harvard architecture is the different one. Okay, good. I was obviously had too much coffee when I made this this presentation. So here's my little diagram. Again, this is not what CPUs actually look like. What is that word beginning with A, which accurately describes what this is an example of? Yeah, it's an abstraction. Abstractions are necessary because if we don't remove unnecessary data, things get cluttered, right? Now, you should recognize the ALU and the CU, they are the same thing, right? ALU is still handling mathematical functions and logical functions. Control unit is still handling the flow of the FDE, still handling the transfer of data between registers in the CPU. Okay. The only difference between the von Neumann architecture and the Harvard architecture is the fact that the Harvard architecture contains separate memory stores for instructions and for data. So when you fetch your instruction with a Harvard system, you go to this instruction memory on the fetch. Anytime that you need to store data or you need to fetch data as part of the instruction that you are executing, you go to the data memory. With the von Neumann architecture, instructions and data are stored in the same memory. No, it does not remove the need for the decode stage. You still need to decode the instruction. Because remember, the instruction is split into opcode, address mode, and operand. Yeah, the control unit still needs to split that up. It still needs to say, right, what's the opcode here? What's the mode of addressing? What are the modes of addressing that you need to know out of interest? Can you just write them in the chat there? There are a number of modes of address that you need to know about. So the opcode, the mode of address, and the operand. I'm eating a Fox's Glacier fruit. It's very tasty. Oh no, no one knows the modes of address. Direct is one of them, yeah. Direct is the one that you will use most of the time. Immediate is another one. Indirect is another one. Are there any more? There are many more, right? But I mean, immediate, direct, and indirect are the main ones that you need to know about. Yeah, index addressing is the other one. Index addressing is the other one that you need to know about. There are plenty of others, depending on your CPU that you have. So, for reference, I think you should know this, but direct addressing is where the operand is an address which contains the data that you are going to use. Immediate addressing is where the operand is literally the data that you are going to use, so you're not going to fetch it from memory. Indirect means the operand is an address which holds another address which points at the data that you want to use. And index addressing is where the operand is an address, and there will also be an index register, a value in the index register, which tells you what offset to go to from that memory address. Okay. So Harvard. Instruction memory, data memory, separate memory stores, which means there will be a separate address bus and data bus for the instruction memory, a separate address bus and data bus for the data memory, and they can have different bus widths. Okay, so remember I said the bus width is just how wide the data connection is. I can demonstrate this for you. If you just bear with me, let me pull up my... oh, it's a fox. I always wondered what that icon was. Okay, it's a fox. Let me just pull this up. Get me whiteboard. Hopefully you can see that all right. So, no, don't do that. Paintbrush. Here we go. This is the instructions. Right. And here we have the, let's call it the CU, right? If we are passing data from the, I'll put mem, from the memory to the CU or back again, if we have a bus width of 1, right, it means we can transmit 1 bit along that bus. Now, obviously, 1 bit, pretty small. You know, there's not an awful lot you can do with that data. If, however, we have a bus width of 8, then effectively, instead of just like 1 line, we end up with 8 lines. Yeah? I don't know how many I've drawn at this point. 1, 2, 3, 4, 5, 6, 7, 8. Right? Which means that in a single transfer, we can transfer 8 bits. Which means that the instructions could potentially be something like 0, 1, 0, 0, 1, 1, 1, 1. Okay, maybe this might be the opcode. That looks like a pood. I'm sorry. And this here could be the operand. Okay. If we had a 16-bit bus width, 4, 5, 6, 7, 8. 16-bit bus width means we'd be able to transfer 16 bits in one go. That could potentially give us more space for more opcodes, more operands, more variants. Be careful here, George. 256 instructions, no. It depends on how wide the opcode width is. Remember, your instruction contains both opcode and operand. If you only have 4 bits reserved for the opcode, that's 15 instructions. Okay, because presumably we need to reserve some space, and I haven't even factored in the addressing mode here either. Okay, so if we had 16 bits though, we could have 8 bits for the opcode. You know, which would be 256 different instructions. We could have 8 bits for the opcode. We could have 2 bits for the address mode, maybe, and then we could have 6 bits for the operand, or any variation of that. Does that make sense? So the more, the higher your bus width, the larger the word that can be transferred there. So maybe that there is our opcode. Then we have our address mode there. Address mode, and we have 2, 3, 4, 5, 6, and there we go. So we can fit in larger words. Now it might be that you don't need lots of different instructions. Maybe you only need 1 or 2 instructions, right? So if I just rub out my my bus there, Maybe you only need 1 or 2 instructions, which means you don't need a massive bus width. So you end up with the maybe you've only got a bus width of 4. Okay, but maybe you don't need many instructions, but you do need big data. Right? So maybe we've only got, like, you know, I don't know, 4 different instructions. Yeah. We might need, this is not a realistic example, but still. But here in my memory store, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'd need a 10-bit wide transfer bus, or data bus, I should say. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. To transfer that. Okay, so the memory on Harvard is separate from the memory for the data in Harvard is separate from the memory for instructions, right? Which means you can have a variable data width for either of the buses. All right. That's that. Right. Moving on. So can addresses used by instructions in the instruction memory refer to addresses in both the instruction memory and in the data memory? No. Well, depends on the instruction, I guess. If it's a branch instruction, then the operand is going to refer to an address in instruction memory because that's going to set the program counter, right? But if it's if it's pretty much any other instruction, it's going to require like data memory. But you don't really need to know the ins and outs of how that works. Okay, you just need to know the fundamental architectural difference there. Okay, is bus width preset or does it change? Most CPUs it is preset, although the amount of space reserved for instructions can vary. But yeah. Right. Oh, what just happened? Advantages of Harvard. Commands can be read at the same time as data is read or written to the memory, which is obviously good. You can have different bus width for instructions and data. So there we go. There's my explanation of bus width. Okay. We established that we do still use Harvard architecture. An example use would be in digital signal processors. That is some research you can do on your own. Right, RISC and CISC. Reduced instruction set computer, right? They contain a simple instruction set. And when I say a simple instruction set, the temptation is to think that a reduced instruction set computer means that, oh, they've only got a few different instructions. That's not necessarily true. Okay, what it means is each, I believe these slides are all up on the classroom already anyway. Okay, what the reduced instruction set means is that each instruction is only doing one thing. It's not a complex sequence of events. Sometimes RISC is known as load store architecture because that's basically what it does. So you wouldn't have a mult function, a multiply function in a RISC CPU. You just do add multiple times. Okay, and that's important because in a RISC CPU, each instruction executes in a single cycle. Okay, takes one full cycle for an instruction to execute. On a CISC CPU, it can take more than one fetch, decode, execute cycle for a single instruction to execute. Because if you've got something like a multiply function or a divide function, which is repeated subtraction, yeah, it's not just doing that one thing. It's not just fetching the instruction, decoding it and executing it and doing that one thing once. It's fetching the instruction, it's decoding it, it's executing it, and in the process of executing it, it ends up doing multiple different things. Yeah, so it can't get done in the same space of time. Load and store are separate instructions. With a CISC CPU, the instruction set is highly specialized. There's lots and lots of very specialized functions. So whereas if you're programming for a RISC CPU, you might end up writing a program which contains lots and lots and lots of instructions that you have combined together to do the things that you need it to do. Whereas a CISC CPU might have an instruction that effectively does that whole program almost in one go, right? But it might be that those instructions are so specialized that you only end up using them maybe once, like in the lifetime of writing programs for that computer. Okay, each instruction takes multiple cycles to complete. Many instructions have load and store as part of the instruction. So with a RISC CPU, you might have an instruction that loads some data from memory. It then adds on some other data, adds on some other data, adds on some other data, and then stores that back into memory. With a CISC CPU, you might have an instruction which pulls something out of memory, multiplies it together by adding it onto itself multiple times, and then stores that back in memory all in one go. Single instruction. Okay. Here's some comparisons. The programs are longer, or the compilation takes longer if you're writing in a high-level language. Potentially faster than CISC, but has higher memory requirements. And if that makes sense, right? If you've got multiple different instructions, they all need to be stored in memory. So the more instructions you have, the more memory is going to be taken up with those instructions. With the CISC CPU, the programs are shorter because they're not using so many instructions. So they're potentially taking up less space in memory. Traditionally slower than RISC. It's difficult to make these sorts of comparisons these days because a lot of the CPUs are kind of a hybrid between the two. But as far as the exam board's concerned, you know, these are the comparisons to make. But yeah, one of the disadvantages of CISC, many instructions are so specific they're never used. You know, you might have a CISC CPU with 100 different functions which are sort of highly specialized mathematical functions, which made sense when the CPU was manufactured. Because it was manufactured for a specific purpose, but it has then become like a general purpose CPU, and that stuff has then become irrelevant. Okay, so not an awful lot more to talk about on Harvard RISC and pipelining, except for the pipelining itself. So Kira, you said you had a question on pipelining. Was it something specific? Was it just like clearing up what a hazard is? Oh, that ain't working. That's not working. How it runs through. Okay, let's have a look and see if I've got an example here. Right. Pretty sure I robbed this picture from Wikipedia, so there is my credit to the creator. John Wikipedia made this. Here we have a number of instructions, right? We've got a green instruction, we've got a purple instruction, we've got a blue instruction, and we've got a red instruction. Okay, so you got to imagine each of these sections is like the state of the CPU having run through a number of clock cycles. Okay, so we start off. Here are our instructions waiting in order to be done. And you can see the first one up is the green one. So first of all, we do. By the way, it says clock cycle up here. It's more the particular stage of the clock cycle, if that makes sense, right? So first of all, we're fetching the green instruction. Cool. So far, so good. Makes sense, right? After we've fetched the green instruction, we have to decode it. But while we are decoding the green instruction, we can be fetching the purple instruction at the same time. Okay? So up to this point, hopefully that makes sense. Now, the issue here is we are not able to decode the purple instruction yet because of something that's happening during the execution of the green function, the green instruction, I should say. So we're executing the green instruction. We can't decode the purple one until that has been executed and written back to memory. Okay, so now we're at the stage where we've written back the green instruction. We can't do anything. We're not executing anything because nothing's been decoded because we had to pause. There was that delay in there. Okay, and then now we're able to decode the purple instruction. The most likely reason for that happening is that we have to wait for the response from this instruction before we're even ready to carry out the next one. It might be something along the lines of the purple instruction relies on data from the green instruction, and so we can't even begin to execute that until the green instruction has been completed and that data has been updated. Okay, so we write back the green instruction. Meanwhile, we are decoding the purple instruction, and while we are decoding the purple instruction, we are fetching the blue instruction. Okay, now after we've written the green instruction back, that instruction is completed. We still have that delay in the system, so there's not going to be any write back at this stage. But because we decoded the purple instruction last time, we are now ready to execute the purple instruction. While we are executing the purple instruction, we can decode the blue instruction. And while we are decoding the blue instruction and executing the purple instruction, we can be fetching the red one, and so on and so forth. That's basically how it's going. So all of this stuff is happening simultaneously, but the nature of things like race conditions, hazards. So a hazard is any potential problem that could occur. In the context of threads, a race condition or a deadlock would occur in that kind of situation. Yeah, and that's why these sorts of delays have to be put in there. That's why. I mean, it's very similar. It's very similar to the concept of database transactions. You know, transactions on a database. If you are planning on editing data which is in a table which is currently being modified by another process, you've obviously got to wait for that process to finish before you can start editing it. Okay, it's not. It's similar, but this is purely executing instructions. Is it sorted into a stack in real life? I'm not sure what you mean by sorted into a stack here. Obviously, this is a purely abstraction. This is just a diagram to give you a visual representation of what's going on. The data, it doesn't actually look like this or anything. And in terms of the positioning and stuff like that, this bears no resemblance to any physical alignment or anything like that. Okay. Cool. So, that is. I'm not going to make you do stuff over the holidays because that's out of date. Right. So let me just have a look. See at my thing, my bob. Here we go. So, does that? Those of you with questions about RISC and CISC, does that clear that up for you? And those of you with questions about bus width, Harvard, pipelining, does that clear all that lot up? Is that good? You guys still on? Yes. Yes. Good. Good. Right. In which case, the slides on the classroom. I'm pretty sure I just. Oh no, I didn't actually click upload. They're there now. Those ones there. But as I've said many times in the past, do not rely on my classroom slides always being available to you. You need to be able to be making notes accurately during the lessons. I know it's a bit late for that advice, but you know, don't become dependent on your teachers is what I'm saying. Be independent. Right, so that's all up there now. Let's have a look-see at the next thing. What is the next important thing to go over? Yeah, that's fair enough. But also remember as well, you don't need to copy everything down word for word. You know, just making quick notes, abbreviations of words, and then being able to copy it up and research in your own time is the way to go. So let's have a look-see. Get rid of that. Right, we've got risk and CISC. I can now knock off. Boom. Bus width, von Neumann, and pipelining. I can knock off. Boom. Right. Right. George wanted an example of the merge and the quicksort. We can do that quickly, and then what we'll do is go over the database stuff. So I can. The reason I say I can do that quickly is because if you just bear with me, I think it's this. Or is it that? Okay, for some reason my internet no longer seems to work, but it obviously is because I'm still online. Who knows what is happening here? Okay, there we go. Go there. Right, are you guys still with me? Internet freak out. Can you see this all right? Yep, good. Right, okay. Here's my deck of cards. Let's shuffle this deck of cards. Right, the merge sort. Let's go through the merge sort quickly. I'm going to use 9 cards. Let's find out what they are. Okay, so obviously in a computer system you're not dealing with cards, you're dealing with lists, but this is the easiest way to visualize it. So to start off with, you would have a list containing X number of items. In this instance, we have a list which comprises 10 cards. Is that 10? Have I miscounted? 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 cards. There's my 10 cards, right? What is that? Let's... nope. Okay, cool. Oh, I see. It's only just loaded in. Brilliant. Good. Okay, right. So we've got 10 cards. First thing that happens with the merge sort is the list gets split apart into, instead of one list with 10 items, it will get split apart into 10 lists with a single item each. You know, or n lists with 1 item each. So the way that it works is by recursively halving the list. Yeah, we start off with these 10 cards. We end up halving the list into 2 groups of 5. There we go. We've got 2 lists comprising 5, and then we recurse into each of those and halve them again. So this time we are going to have a list of 3 and a list of 2. Okay, and we are going to recurse into those as well. We need to split this up into a list of 2 and a list of 1, and then we would split this list of 2 into 2 lists of 1. We don't have to do anything to this list. We now out here, we're splitting this list of 2 into 2 lists of 1. Now we're back out here. We can split this into a list of 3 and a list of 2, and then we recurse into here. We can split that up into a list of 2 and a list of 1, and then we can split that up into 2 lists of 1, and then we're back out here, and so on. Does that? Obviously, that's just the preparation for the sort. I'm going through that because there's a lot of textbooks out there which will give you examples of how to partition the lists. And I think traditionally that's what the system would do. But if you're using Python, you can just use a list comprehension to instantly split the list, and it's no big deal, right? But the important bit is the merging of the lists. So you start out by comparing the first 2 lists, and you are always comparing the first items in each list. So we're looking at this queen and this king. We're comparing the first items in each of them. Because there is only one item in each of them, we're only looking at the sole item in there. We're looking for the lowest one. The lowest one out of these 2 is the queen. So the queen becomes the first item in a new list, which is going to be a list containing 2 items. In some programming languages, you need to set the length of the arrays before you can start putting stuff in there as well. In Python you don't. Okay, it just flexes for you, but in other programming languages you have to set the dimensions of the array. So next we are going to, because we're comparing the king effectively to nothing, the king is going to be the next card to come up. So there's our first merged list. Okay. And next up, we are comparing these 2 lists, the 3 and the king. The 3 is the lowest out of those 2 cards, so that's going to be the first item in our newly formed list. And then we're comparing the king to nothing, so that's going to come up here. And we just proceed in that way until we have merged all of these lists together. In this instance, the 8 is the lower of the 2, so that's going to come up and form the first item in our new list, followed by the queen. And then we're going to have the 3 and the 5, and then we're going to have the ace and the 10. Okay? So each stage, the size of your individual lists is getting larger. You know the list is sorted when you're back to a single list containing n items. So on this pass, we are still comparing the first 2 lists, comparing the first item in each list. So we've got this queen and we've got this 3. The lower of the 2 is the 3. So the 3 is going to come down and form the first element of a new list here. Now you're comparing the first item in each list. So we're comparing this queen to this king. Just because that 3 came down doesn't mean that the queen is automatically going to come down. She is in this case because she is a lower value than the king. So down she comes. Right now we're still comparing the first card in each list. We're comparing this king to this king. In these sorts of situations, you would bring the leftmost card down first because that is going to preserve the relative order of the items. So now this king is going to come down there. So we've merged into a list of 4. Same process applies here. We're comparing the 8 and the 3. So the 3 is going to come down here. The 8 is not automatically going to come down. Because if I bring that 8 down there, then, well, there's nowhere for this 5 to go because the 5 needs to go in between the 3 and the 8. So don't fall into the trap of just saying, okay, cool, well, here's the lower of the 2, that comes down, and then automatically bring that other one down. No. You're still comparing the first 2 items. So we're comparing the 8 and we're comparing the 5. 5 is the next one to come down. Now, because we've got an empty list here, we know that the comparison between these 2 things is always going to favor this list over here. In an actual program situation, you'd still go through the motions, but because of that, it would automatically bring that stuff down. Okay. Next up, What do we do with this list on the end? Well, if there's nothing to merge it with, you know, it just stays as it is. Okay, we keep going through that process. We're going to merge these two lists. The 3 and the 3 are equal, so we're going to bring the leftmost one down first. The queen and the 3 is the lower of the two. The queen and the 5 is the lower of the two. The queen and the 8 is the lower of the two. Queen and the queen, this queen is the leftmost one, so she's going to move there. Queen and the queen is the lower. And then we're just left with these two kings, so they can go back up there. Now we're ready to actually merge these lists. Okay, even though the lengths of the lists are not the same, we can still merge them together. So we're just looking at the first card in each list. Ace is the lowest there, so that's going to come down here. Now we've got the 3 and we've got this 10. The 3 is the lower of the two. We've now got this 3 and the 10. The 3 is the lower of the two. We've now got this 5 and this 10. The 5 is the lower of the two. We've now got this 8 and this 10. The 8 is the lower of the two. We've now got a queen and the 10. The 10 is the lower of the two. And now for the rest of this, there's nothing to compare the rest of these cards to. So they are all going to merge together into our list, which you can see now is fully sorted. Okay. Hey, no worry, Piggin Plays. I hope my stuff was useful, and I hope you're having a good time at university. Right, cool. So, any questions on the merge sort there? Those of you that are interested in the merge sort, any questions on that before I launch into the Quicksort? I will give you a couple of minutes to just type some stuff in there while I go and take a quick comfort break. I'm back. Who does things well? Me? I resent that statement. No, not really. I mean, I think I do things all right. Right, let me shuffle the deck again. I'm going to shuffle all those cards. We'll do the Quicksort now. Or, as they say in America, the Quicksort. So I'll use 10 cards again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, let's have a look at how this is going to work. Okay, so the Quicksort. What you are essentially doing is you are choosing a pivot point and you're aiming to get all of the cards that are higher than the pivot on one side of it, all the cards that are lower than the pivot on the other side of it. Okay, once you've done that, you know that the pivot card is in its final resting place, and then you can do the rest. You can do the same process to all of the stuff on either side of the pivot. So in order to do this, we're going to need 3 pointers. One of those pointers is going to be the pivot, one of those pointers is going to be the left pointer, and the other one is going to be the right pointer. So we're going to choose a pivot at random. It doesn't matter which one you choose. Some implementations of the algorithm will always choose the leftmost card to be the pivot. Some will always choose the rightmost card to be the pivot. Some will always choose the center card to be the pivot. Ultimately, it doesn't matter. Play the dancer. Oh, I'm not playing that. That'd take way too long. I'm going to choose this 9 as my pivot. There's my randomly selected pivot card. Okay, so if this was a list, my pivot pointer would be at index 3, 0, 1, 2, 3. Okay, so what we now do is we start off from the left hand side and we move inwards, checking until we find the first value which is higher than the pivot. First value which is higher than the pivot. Okay, so 5 is not higher than the pivot. The jack is higher than the pivot. Okay, so that is going to be my left pointer. Okay, that's the value my left pointer is pointing at, and it would be index 1, if you like. Okay, on this side I am starting from the right hand side and I am moving inwards until I find the first card which is less than or equal to the pivot. Okay, less than or equal to the pivot. And 7 is the first card. It's literally the first card I was on, right? Once we have settled on these two cards, we are going to swap the positions of them. Okay, the values for the left and right pointer remain the same unless the pivot changes, which maybe we'll get onto. So the jack goes over here, the 7 goes over here, right? They go back into their relative positions there. Now my pointer is still pointing at this position here, still pointing here, and my right pointer is still pointing here. Okay, so I just keep on going until I reach the pivot. I can't go past the pivot from the left. I can't go past the pivot from the right. Okay, remember, I'm looking for values which are greater than the pivot. Okay, so 3 is not greater than 9. 9 is the pivot. So I know that my left pointer is the pivot as well, right? I'm starting here. I'm moving inwards until I find the first card which is lower than the pivot. That is the ace. Okay, now remember, 9 is the pivot card. Yeah, so what happens here is I swap the position of the ace and the 9. Now my pointer before for the pivot was pointing at index 3, right? But because I have moved the pivot, what happens is the position of the pivot pointer moves with it. It essentially becomes whichever pointer we've moved it to. Because my right pointer is the one that's swapping, the card at the right pointer is the one that's swapping with the pivot, my pivot now becomes the right pointer. Okay, so that goes into position. My left pointer is still the same one, so I'm going to start from here. Here is still my pivot card, yeah, but I know at this point, because my pivot is on the right pointer, because I had to reset that there, my right pointer is still on the pivot card there. I'm moving inwards here until I find the first one which is bigger than the pivot. Here we are again. We're at a point where we're going to swap the pivot with one of the other cards. Now as we swap this over, the pivot exchanges position with the left pointer. The position of the pointer pivot now becomes the position of the left pointer. Okay, the card that was at the left pointer takes up the position of whatever the pivot was there. Okay, so my right pointer is at this place here where the queen is. My left pointer and the pivot pointer are the same at this stage. So my left pointer is not moving, it's on the pivot already. Okay, the first card that I find moving inwards, which is less than or equal to the pivot, is this 7. So I'm going to swap them over. Okay, now my left pointer at the moment is on the 7. My right pointer has changed position because I had to swap the pivot. So it's not going to move further inwards. My left pointer is going to move up. Now I'm in a situation where both my left pointer and my right pointer are pointing at the pivot. Therefore, I know that that pivot is in its final position. So I can flip it over. There it is. That's not going to move now. That position is fixed. And now all I do is recursively apply that algorithm to both sides of the list. Okay, this partitioned list. We are now applying the quicksort to this bottom list. So I'll choose this 3 as a pivot. Why not? Let's do that. Okay. First card that I find which is greater than the pivot is this 5. The first card counting inwards that I find that is less than or equal to the pivot is this ace. So they are going to swap positions. Yay, there they go. Okay. Now, Moving inwards, the first card I find which is greater than the pivot is this 7. The first card that I find less than the pivot is this ace. So they are going to swap positions. There we go. Moving inwards, I hit the pivot, so my left pointer rests on the pivot. Moving inwards here, I hit the pivot, so my right pointer lays on that pivot. And therefore, if they're both on the pivot, it's done. That is not going to move again. Okay, now I'm doing it with this list. Again, randomly choose a pivot. Here we go. By the way, it's around this point where you can start saying stuff like, well, it's a list of 2 items. So just check to see if one's greater than the other. You can do that, right? But if we're going the whole hog, quicksort all the way down. Choose a pivot. I'm choosing this ace. Obviously, my left pointer is already on the pivot. It's not going to move any further than that. My right pointer is checking to see if it's less than or equal to. Well, that is less than or equal to, so they are going to swap positions there. And my pivot is still this one. Okay, so moving inwards there. Both of my pointers are ending up on the pivot. There we go. Now we're left in a situation here where we have a list containing a single item. By default, that is sorted. Okay, so I know that that's in its final position. Okay, now I'm tracing my way back up the recursion stack here, and I am now onto this list here. Going to choose a pivot. Let's choose the one in the middle. First card greater than the pivot is this one here. First card less than or equal to the pivot is the pivot itself. So those 2 cards are going to swap position there. My right pointer is pointing here. My left pointer and the pivot are both on this card here. This is not less than, so both my pointers are now pointing at the pivot. So that is in its final position. Choose a random pivot. Here we go. We've got a 7. Is this card greater than the pivot? Well, it's on the pivot, so that's where that pointer is going to stay. This card is less than or equal to, so they are going to swap. There we go. Boom, they have now swapped. This is still the this is still the pivot card. So my right pointer, my left pointer end up both here. That's in its final position. That's a single list of 1, so that's in its final position. And now we're back up to this list of 3. Here we go. Choose this as the pivot. Where are my pointers? Well, this is the first card greater than the pivot. This is the first card less than or equal to the pivot, so we're going to swap both of those over. The left and the right pointer are both pointing at these 2 cards here. This is not greater than the pivot, so my left pointer is now pointing at the jack. This is not less than or equal to the pivot, so my right pointer is pointing at the jack as well. So that's in its final position. Flip him over. This is a list of 1 item. Flip him over. This is a list of 1 item. Flip him over. And now if we reveal all of the cards, you will see that they are all nicely sorted. And that, ladies and gentlemen, is the Quicksort. Makes sense, right? Cool. Right. So Quicksort done. Let me tick that off the list of stuff as well. Merge and Quicksort both done. Boom. We're getting through this like wildfire. Right. Dictionary compression, foreign composite keys. We'll do the foreign and composite keys thing quickly because that is a quick thing to do. So just bear with me. Ein Momento. Let me find the database presentation that has the stuff about composite keys in. This is very quick, by the way. I mean, I say it's very quick, and then my internet. No, there we go. Right. Possibly in this one. Let me just have a quick look. Yeah, here we go. Right. Do. Oh no, what have I done? Cool. Right. Here we go. It falls under, well, it was in my presentation on database normalization. Database Sekika. Right, here we go. Let's imagine we're in this sort of situation here, where we have a it doesn't necessarily, right, well, I'll skip forward to this. We've added our link table in here. We have a one-to-many relationship between film and role. We have a one-to-many relationship between actor and role. Right? Each film contains many roles. Each role can only be in one film. For example, the role of Jaws the shark is only available in Jaws film. Right? The role of Jaws the shark in Jaws 2 is technically a different role. In the same way that Luke Skywalker is a role in the film Star Wars, that particular role, Luke Skywalker in Star Wars, only exists for that film, Star Wars. Even though the character Luke Skywalker appears in Empire Strikes Back and Return of the Jedi, technically they would be different roles. Does that make sense? Each actor can play many roles, right? Each role can only be played by one actor. Harrison Ford played both Indiana Jones and Deckard in Blade Runner. You weren't expecting me to say that, were you? You expected me to say Han Solo, but he played them as well. He played all of them, right? Those roles have not been played by anyone else because it was Harrison Ford in those movies. Okay, so when we put this into a database table, each of these tables, the film table and the actor table, will have a primary key, right? You understand primary keys, yeah? Just give me a yay or a nay if you understand what a primary key is. Yay, right. So, first of all, let's talk about foreign keys. Ignoring for now, I was literally about to put my hand over the screen, but then I realized that me covering up the screen would not stop the thing being visible on the stream at home, right? Anyway, let's just consider film and role, right? One film has many roles. Each role can only appear in one film. And so, in order to identify which film the role appears in, each role, as well as its own primary key, will also have a foreign key, which is the primary key that has been imported from the film. Right? Which film is the role of Luke Skywalker in? Well, we wouldn't say it's in Star Wars. We'd say it's in film ID number 1, which might be Star Wars. Okay? So the foreign key is whichever primary key has been imported into the table in order to link it back. And you will find that the foreign keys appear in the tables with the crow's foot on the ERD. Right? If there's a one-to-many relationship, you will have a primary key in both of those tables. You will have a foreign key in the table with the many bit coming from the table with the 1 bit. Do I have... yes, so... no, that's not the one that I wanted. I might need to open a different table. Different presentation. Bear with me 1 second. Perhaps in this one. Yes. Right, here's an example. Right. We have a list of users. We have a list of orders. Okay? Each user can place many orders. Each order can only be placed by one user. Bob has user ID 1. Jim has user ID 2. Alan has user ID 3. Okay? Note, user ID is the primary key for users. Order ID is the primary key for orders. But note, there is this ID in here. This is the foreign key, which has been imported from the users table, which is used to link each individual order to the user that created it. Okay, so we can see here, order ID number 1 was placed on the 420, lol. Was placed on the 20th of April 2018 by user ID 2. Now this allows us, rather than putting the name in here, if we just put the ID in there, it means we can look up ID number 2 in this table. We can see that Jim placed that order. Order number 2 was also placed by Jim. Order number 3, however, was placed by Bob. Okay, so the foreign key is the primary key from another table which is imported into your table in order to link the two tables together. Does that answer your question about foreign keys, Kira? Oh no. Is it too late? Too late. Yes, right. Composite keys. Cool. So, knowing what you now know about foreign keys, right? We have a film contains many roles. Each role is only present in one film. An actor can play many roles. Each role is only ever played by one actor. In the role table, you are going to have a foreign key from the film table. You are going to have a foreign key from the actor table. Okay, because we need to know which film does this role appear in. We also need to know which actor is playing this role. Now, we could structure this table and have role ID and then film ID and actor ID. But because this is merely a bridging table, merely a link table, right, which we have used in order to get out of that horrible fan trap, many-to-many relationship, okay, what we have to do is either give the link table its own primary key, which is going to take up additional memory, or what we can do is make the primary key the unique combination of the two foreign keys. Let me show you what I mean by this, right? Actor ID and film ID are both foreign keys from the other tables. The combination that they form will be unique. Okay, they will be unique. Here we go. Let's have a look at this. If I've got film ID 0, actor ID 0, right? This role is part of, let's say film 0 is Star Wars. So this role exists in Star Wars. Let's say actor 0 is Harrison Ford. Yeah? Should I say Harrison Ford or should I Mark Hamill? It doesn't really matter. Okay? There is no other combination which is 0, 0, right? Mark Hamill played the role of Luke Skywalker in Star Wars. Okay, that's no one else played the role of Luke Skywalker in Star Wars. Is this making sense? Yeah. Likewise, film ID 1, maybe that's Indiana Jones, and maybe actor number 1 is Harrison Ford. I don't know. And then film ID 0, we've got another actor here, right? So the combination of these two foreign keys together is unique, and that combination of both of them together can be used as a primary key. So instead of a single field, the primary key field, you have two foreign keys, the combination of which is unique, and that combination of the two together forms the primary key for that table, and that is what we call a composite key. Okay, does that make sense? Excellent. Excellent. Right. We're gradually working our way through this. What time is it? Nearly 7:30. Okay. Right. We've done foreign and composite keys. Farrell, laws. Was there anything particular about the laws that you wanted to know? Is Farrell still here? Has he gone away? Okay, maybe we'll come back to that. So what else is on the list here? Let's go over hashing quickly. Let's go over hashing because Kira mentioned hash collisions. And we will just go over that. Give us a second. Dun, dun, dun. Right, here we go. Cryptographic hashing. Presenter view. We have got this here. Yeah, okay. I'll explain. You understand the concept of hashing, though, right? The idea that you are taking data of an arbitrary size and you're mapping it onto data of fixed size. Yeah. So you could take the entire works of Shakespeare, feed it through a hashing algorithm, and produce a hash which is 64 characters long, potentially. In the same way, you could take just the letter A and run that same letter through the same hash algorithm, and you would get a map of 64 characters, for example. It is not encryption. Yeah, it is. Asymmetric. Are you saying asymmetric encryption because that's what you think it is, or because that's what you want me to go over? Right? You cannot use hashing. You cannot use hashing as a method of encryption because it is a one-way process. Right? It has a use in cryptography. It has a use in cryptography in the sense that it is used to store passwords, but it's not used to store passwords so that they can be decrypted. Okay? It is used to store passwords so that we never have a plain text representation of the password. What we do is, instead of saying, oh, my password is apples, and then when the user types in their password, say, if password equals apples, then, you know, what we're doing is we're taking apples, we are hashing that, right? And then when the user types in their password, what we would do is say, if password dot hash or something, or if hash password equals like whatever the hashed version of apples is, then we can compare that there. Okay, it's very important that you understand hashing is not used for encryption. You cannot encrypt, well, I mean, you can encrypt data, but you won't be able to ever get it back again. That's sort of like the point. Okay? So there are two uses. One use is in lookup tables. Right? This is what happens with Python dictionaries. The key gets hashed. okay, that hash value gives you a location in memory where the value, the associated value, is stored. Okay, so you know in a list, you've got a list, you've got index 0, index 1, index 2, index 3, index 4, right? With a dictionary, you can have whatever you want the keys to be. The place where the associated value is stored is based on a hash of the key. So if I have my key as Alice, right, performs a hashing algorithm on that to get a location in memory, which is where the value is going to be stored. It's used in databases quite a lot because if you use hashing in order to store data, it means you can look it up very quick. Okay, you don't have to scan through tons of stuff. You don't have to read through stuff sequentially. You just take that value, you perform the hash algorithm, you look it up, right? It increases the speed of table lookups. Okay. The things that a hashing algorithm need to do, right? Always produce the same hash from the same message, right? And this is where the concept of hash collisions comes in. I'll give you an example in just a moment. Where's the thing? Here we go, right? If I take the input Fox, I run it through this cryptographic hash function and I get this output here. Okay, that's cool. You'll notice that all of these outputs from this hashing algorithm are different to each other. Even though there's a tiny change in the input text, there's a massive change in the output text, right? A hash collision is when you have two different input texts or input values, and the output from the hashing algorithm makes them map onto the same hash. So you can see here, does this enters on AS level? Is this part of the AS level? I do not know. I think so. It's definitely part of the A level. I am not entirely sure if it's on the AS level as well. I don't have the AS spec in front of me. Okay, so we've got the word Fox here, yeah? It maps onto DFCD 3454, BBEA, 7AAA, 751A, 696C, 24D9, 7009, CA99, 2D17. If I had a different input, like, I don't know, Coyote or something like that, and I ran that through the hash function, and that also mapped onto DFCD 3454, BBEA, 7AAA, 751A, 696C, 24D9, 7009, CA99, 2D17, then it means that two separate inputs end up with the same output. That is what a hash collision is. Obviously, hash collisions are a bad thing if you are using cryptographic hashing to store your passwords, because it means that potentially someone could type in a password which is not the stored password, or not the password that the user created, and if it maps to the same hash value as the password that the user created, it means that the other person is going to gain entry. Does that clear up your question about hash collisions? Excellent. Right, that's hash collisions done. I'll just reiterate as well that cryptographic hashing algorithms are not just used for keeping data safe and secure, right? Remember, they're not encryption. They are used to hash a password so that we don't have to store that in plain text. It is a one-way operation, but also hashing is used in lookup tables. It's used in databases so that we can store reference points in memory based on a particular key. Yeah, you take your primary key value, you hash that primary key value, it might give you a memory address, which is where you can store some data. Yeah, so we can have these very rapid reference points. Okay? Do I need to go over anything else? No. I don't think I need to go over salting. I'm guessing you guys are fairly familiar with that, and it's probably not going to come up much. Don't worry about dictionary compression. Don't need to know LZW, not LMZ. But yeah, you don't need to know the ins and outs of that. Okay, it was purely a practical exercise so that you could see some of the application of that particular algorithm. Okay, right. Right. How long we got? How long we got? I don't know. We're done there. Right. Tyler says programming. All of the programming. Can you be more specific? Right. Bearing in mind, you need to know how to write Python, how to write pseudocode, how to read pseudocode, how to write assembly language using the little man computer. You also need to know how to write HTML, JavaScript, and CSS. JavaScript and HTML. Right. So, first of all, first thing that I will show you is this. In the spec, towards the end of the spec, SQL, again, let me know specifics. I do not have time to teach you the whole of SQL, but if you let me know the specific bits that you're not sure of, I can help you out, right? Okay, so back at the spec, there is their guidance for writing pseudocode. You will notice that a lot of it looks very similar to Python. X equals 3, name equals Bob. Note they are using quote marks there to assign strings. Specifying variables as in the global scope, they will use the global keyword. So global user ID equals 123 means that the variable user ID will be able to be used at any point during the entire program. Variables can be typecast using the int, strut, and float functions, exactly the same as Python. Okay, so this is all pseudocode. The print command is exactly the same. The way that they do input is exactly the same, right? The differences lie with their programming structures here. Iteration, that's loops. For I equals 0 to 7, right? In Python, we would do for I in range 8. One thing to be very careful of. The exam board pseudocode uses inclusive bounds. Python uses exclusive bounds for the upper bound. It uses inclusive for the lower bound. Okay, so when they say for I equals 0 to 7, it means 0, 1, 2, 3, 4, 5, 6, 7. It includes that. In Python, you would do for I in range 8, which would start at 0 and go up to but not include 8. Also, at the end of a for loop, they will put next I. That basically means that this is the end of the for loop. Go back up and move I onto whatever the next value is. Okay, so if you see that next I, that is just the end of the for loop. They will not use end for. That's not a thing. Next I. They will say next and then the name of the iterator variable that they are using. The way that while loops work, pretty similar to the way they work in Python, except at the end, they will have end while. Can I just do a control expression thing? I don't know what you mean by that, George. What do you mean by a control expression? How would you recommend revising those and regularly programming those? Just write some code. For SQL, get a copy of My SQLite Studio or whatever it's called, SQLite Studio. Create some databases and run some queries on there. W3 Schools. W3 Schools has a lot of stuff on SQL. W3 Schools is the place to go if you want to find out HTML, CSS, JavaScript, SQL, and there's some Python on there, but it's not amazingly complete. Okay, George, just tell me, explain what a control expression is. Let me also explain the difference between a while loop and a do until loop. A while loop, you will only enter the while loop as long as this statement is true. A do loop, you always do it at least once, even if the statement is false. Okay? So for example, if you declared a variable, if you said answer equals computer before the start of this loop, it would still enter this loop, right? But before the while loop, if you said answer equals computer, it wouldn't even bother entering that loop in the first place. Okay, so do loops, do until, is exactly the same as a while loop, but it always does it at least once. Right, you've got to make sure that variable declarations and stuff like that are clear as possible. Don't try. My recommendation: do not try and do any fancy code stuff. Right, the people marking your paper are not going to be impressed by like fancy code juggling or anything like that. They are going to be looking at does it have this for loop? Does it have these variables? Does it do this? Does it do that? Right? Lay it out as clearly as possible. Right? If you're familiar with list comprehensions in Python, I would recommend not even using those. Write the for loops out in full. Right? The reason is the people marking this stuff are going to be going off their rubric that they have. They're not necessarily experienced programmers. You know, you will find most computer science teachers across the country don't really have a great amount of programming experience. The people marking the tests are not always even computer science teachers. Okay, so don't try and put any creative flair. Save if you want to use if you want to show off your creative flair in your programming, the coursework project is the time to do that. Okay. Right. The other thing as well about the pseudo code, if and else, pretty much exactly the same as in Python, but use else if instead of elif. You know, and there's an end if at the end. Generally speaking, though, as long as your code is readable and is the indentations are in the right place and you've got the logic fine, it's not going to be that big a deal. Okay, so I wouldn't worry too much about it. By the way, newest versions of Python have introduced the switch block. You can use switches in Python now. How sick is that? No problem, Kira. Get a good night's sleep. Best of luck tomorrow. I would recommend, rather than me going through all of this stuff now, I would recommend just going over it yourself and just having a look at this stuff. Okay. How what? How'd you do it? I'm pretty sure. Let me just check something out. I think it's in Python 3.10. It's fairly similar to the way it works in C++. To what extent do we need to know JavaScript? That was the next bit that I was going to get onto. Down here. Right. This is what you need to know for HTML. You need to know how to use the HTML tag, how to use the link tag in order to link to a CSS file, how to use the head tag, how to use the title tag, how to use the body tag, how to use the H1, H2, and H3 tags, how to use the image tag, how to use the A tag to put inline links in your document, how to use the div tag, the form tag, the input tag, the P tag, the LI tag, the OL tag, the UL tag, and the script tag. Those are the only ones you need to know, right? So if you have the knowledge of a 15-year-old in the 90s making his own web page about Doom, you know, then you already know more than you need to know for this. Any additional elements will be explained in the question, right? Those are the only ones that you need to go over. And by the way, this specification is shared up on the Google Classroom. What are div and form? Div is a tag which on its own doesn't do anything. It just specifies a division within your page, right? And what it does is you can apply styles to that division. Okay, let's go to, I've got an idea. I've got an idea. Let's go to W3 schools. So you can see here, we've got an HTML page here, and we have some CSS styling here. My div. We are specifying the border to be 5 pixels, outset red, background color light blue, text align is going to be center, right? We now have this div. This div is a division, which basically means, anything which is in between this opening div tag and this closing div tag, just apply whatever style is applied to the class myDiv. Okay, so if I run that, you can see, oh look, the div element. Here is my div here. I could create another div around here. Let's do if I just do a blank div like this and include the P tag in there. Helps if I actually close the tag. You'll notice it should look exactly the same while I've done that. No difference whatsoever because I haven't applied any style to it. The moment I say class equals my div, the moment I do that, oh look, now it's applied that style to everything that's inside that division. Okay, that's all the div tag is. On its own, it does nothing. It is there so that you can style specific parts of the page. Very, very useful for getting boxes around things or positioning elements within your page. Okay, and form. The form tag is used to include various inputs on your page, right? So if I go to form, here's the form tag. The form tells you what page you are going to call when the form is submitted, and it acts as a container for all of the different inputs in the that you're putting on your HTML form. Okay, so for example here we have the form contains a label, it contains an input, a label, an input, an input. So all of this stuff here is part of the form, including the submit button. Okay, when I click submit, I can see that it's going to send my data to actionpage.php. Okay, so let's say my first name is Elsa and my last name is Shrek. I submit that and we can see the submitted form data was this stuff here. Okay, so all the form tag does, it has an action. Action merely points at the server-side scripting page, which is going to run your information, or it might point at a client-side scripting page to pass the information onto. It also acts as a container for all of the individual inputs. All right. So there we go. But the only inputs that you apparently need to know are is just the standard input. So input type equals text, input type equals submit. That's all you need to know. You don't even need to know text area, radio buttons, select. You don't need to know any of that stuff. They will tell you about that. Okay. In terms of CSS, you are expected to know how to apply specific styles to specific tags like this. This is going to apply the color blue to the H1 tag. Okay, you need to know how to apply in classes, so put in the full stop in front of it. .info box, that is going to apply this style to anything that has class equals info box in its tag. And then IDs, starting with the hash symbol, means that the single item that has ID equals menu in it is going to have this style applied to it. The only properties that you need to know are background color, border style, border width, color with named and hex colors. So remember, the hex colors are going to start with a hash symbol. Hash FFFFFF is white, for example. Font family, font size, height, and width. I would recommend you have a quick scan through this and maybe have a look up at those things on W3 Schools to have a play around with them. JavaScript. The only JavaScript that you need to know input. Well, you don't need to know any JavaScript input because it's all based on the HTML forms. Okay, so you're going to be pulling stuff from the HTML forms. Output. Chosen element equals document.getElement by ID. This is how you pull the information out of your form. So things to remember. Get element by ID, lowercase g, capital E, capital B, capital I, lowercase d. So get element, document.getElement by ID example. What that is going to do, it's going to look at whatever element you have ID equals example on, and it's going to inspect that element, right? You will probably also need value. This is basically it. Interesting. Thanks for that, user one. Chosen element.innerHTML equals hello world, right? Setting the output, if you use, I mean, you don't have to do this on 2 lines. You could say document.getElement by ID example.innerHTML equals, and that's the way that you can get JavaScript to update stuff there. Document.write will overwrite the entire page, and alert, and then whatever you put in the brackets there, it's just going to make an annoying text box, like box thing pop up. Those are the 3 JavaScript, or rather the 4 JavaScript commands that you need to know. You do not need to know any more than those ones. If they use any of those in a question, any additional ones, they will explain it to you, right? So don't get stressed out over the JavaScript. I'm sure you can spend like 15 minutes just like going over those 4 elements because those are the only ones you need. Okay? Now then. I see. Cool. There we go. That's yeah. Don't worry. I've silenced the miscreant. It's got nothing better to do with his time. Right. You definitely need to know all of these, by the way. Every single LMC command, you need to know what the mnemonic is, and you need to know what they do. Okay? Yeah, obviously proven that he hasn't matured any in the past year or so. You've got add, and you're adding stuff. Sub is subtract. Sda is store. LDA is load. Remember, you are storing data from the accumulator into the location in memory. LDA, you are loading data from memory into the accumulator. Branch, always branch. BRZ, branch if 0. BRP, branch if positive. It is checking the accumulator to see what the value is, right? I just wanted to point that out. So always branch obviously is not checking anything. Branch if the value in the accumulator is 0. Branch if the value in the accumulator is positive and it counts 0 as a positive number. Okay? So just be careful on that one. Imp is input, out is output, halt is end program, and dat is not really an instruction. It is merely a mnemonic that allows you to label a memory location. Okay, you absolutely need to know those, and you absolutely need to be able to write programs with them. So, after all of that, I know that Tyler said, I want to know all the programming stuff. I do not have enough time to teach you all the programming stuff. If there's one particular programming thing that you want to know above all others, what would that thing be? Let me know. What's the difference between Sda and Lda? Lda, the operand is an address in memory, and whatever data is stored at that address will be fetched, and then it will be stored in the accumulator, right? With Sta, you take the value that is currently in the accumulator, and the operand gives you a memory address. That value will then be stored at that memory address in memory. So it's like LDA is pulling things from memory, STA is pushing things to memory. Are we all, is it all good? Any further questions? Farrell, does that clear up any concerns you might have had about JavaScript? I appreciate that I went over that like fairly quickly without any like explanations, but does that sort of like, oh, laws, yeah, good, remember, yeah, well remembered. I did ask, yeah, Farrell was missing at the time. Right, so which laws do you want to go over specifically, and to what extent? JavaScript and HTML makes sense. Excellent. Good. So what about the laws did you want to go over? To what extent do we need to know about them? You need to... It's unlikely that you will be asked any questions about like, oh, explain what this act of law does. It's more likely that you will be expected to apply your knowledge of them to specific situations. So in a question about I don't know, some ethical thing, so and so is planning on building a robot to terminate all human life, discuss the ethical implications of this. You might think, oh well, if the robot is using people's personal information, then obviously that data needs to be stored safely and securely in order to like conform to the Data Protection Act 2018. If someone hacked into the killer robot and accessed that data, then depending on the type of data that was stored, the creator of the killer robot would be liable to a punishment of 10 million euros or 2% of annual turnover, whichever is higher, or 20 million euros and 4% of annual turnover, whichever is higher. Wow! Imagine having so little going on in your life, hey? So yeah, it's you won't have to say this is the law, that's the law, yada yada yada. what you will need to do is like explain that in context. So on a basic level, you need to know what each of the laws protects against. You need to know what the different violations of those laws might be, what the punishments for breaking those laws would be. Does that help? Is there any specific elements of the laws that you want me to go over? Yeah, I mean, you don't necessarily need to, like, remember as well, those punishments are the maximum like punishments under the law as well. So it would all be like considered on a case by case basis. At the very least, you should recognize what the individual tiers of, like, for instance, the Computer Misuse Act, the 3 different tiers, being able to differentiate between the severity. Is useful. Actually knowing what the specific punishments are, those are the sorts of things that are sort of like get you, if you're already in the top mark band, they will get you even closer to the, like, the top marks for an essay question, for example. Is that all good? Yep, cool. Right. Top tips for just like general exam stuff. Make sure you read the paper thoroughly before you start. Make sure you like choose your battles. So answer the easiest questions first. Do make sure that you double check your work, especially when it comes to things like writing code and stuff like that. It's a good idea to, once you've written it, maybe move on to answer another question and then come back to it. Read through the whole paper before you start. I've already mentioned that. Read the question thoroughly. Make sure that you're actually answering the question that has been asked, rather than the question that you think has been asked. Underline or highlight like specific keywords as well, so that you know what to talk about. Unfortunately, on the essay questions, the quality of your written English is assessed, so aim for no spelling mistakes, no grammatical errors and stuff like that. Write clearly, use a separate piece of paper if necessary. If you go wrong, cross it out so that it can still be read, okay? And if necessary, go onto another piece of paper to answer the question. Please make sure that you number what question it is. Don't just like spread things all around. Show you're working on any questions that involve, like, converting between different numeric formats and things like that. The obvious stuff that I say every time, but people often forget about. Most importantly of all, don't get super stressed out about it. The more stressed you are, the worse your performance is going to be. These are mocks and they are sort of kind of important. Oh my God. Why is there so much anti-Semitism going on here? Anyway, let's not. I know people with, I don't know, less going on in their lives than it just boggles the mind, doesn't it? Imagine having a life so boring that you hop onto an educational live stream in order to, like, ask racist questions. How odd. How odd. Anyway. Yeah, nothing more for me to say. Get a decent breakfast, get a good night's sleep, and come and find me after you're done so that you can either call me a horrible man for setting a test so hard, or call me a wonderful man for setting a test so easy, or just say, I don't know how well I've done, and maybe just let me know how you got on. That's basically it. And without further ado, it's time to end. It's time to. Will you? Yeah, I will. Right. So I will be in my room from about 7:30 until 8:15, because then I've got to go and do my tutor group. So I'll be around from about 7:30, and that's it. All right. Oh my. Yep. These people, man. These people. Okay, cool. Right, wicked. Well, best of luck, and I will see you all later.